Hello, quick video on stationary points and differentiation. Quite often we're looking at some sort of function and we want to know where the maximum and minimum points are. So for example, if we were looking at the flight of a cricket ball, we'd like to know where the maximum height is and how far away from us that is. And to do this, we therefore use differentiation. Now the points that we're looking at in these cases, these called stationary points, so the maximum where it's reached its maximum height, or it could be a minimum. Those are two we're obviously interested in. But there's actually a third type of point called an inflection point, which I'll try and explain as we go through. Okay, so let's work out what the properties are of these stationary points. Well, let's have a quick look at this maximum up the top here. Look at the gradient. So on the left hand side of this maximum, the gradient is positive. This is going up. And on the right hand side, it's going down. So at some point in the middle, it's actually going flat. It's going level. Yeah, it's not going up anymore. It's not going down. It's stopped. And that will be the maximum point because it's not going up anymore. And it's not started going down, yeah? So at that point, the gradient, the dy by dx, is 0. And that's also true of our minimum point down here, because the gradient's going down on the left-hand side of the point, it's going up on the right-hand side of the point. So at the point of the minimum, it's just going flat. It's going across. The gradient is 0. So, but there's also one other type of point we talked about, I mentioned, which is this inflection point. So at this point, to the left hand side, the gradient's going up, then it sort of levels off and goes flat for a bit, and then it goes up again, and it could do the same thing the other way around. So those are our 3 points, but in all of these cases the key bit is that the gradient is 0, yeah, at each of these points. Now the question is, how do we distinguish between them? Okay, and the way we do that is by thinking about what's happening to the gradient. So if we go back to our maximum point on the left, it's going up. The gradient is positive on this left-hand side. It goes flat and then it goes down. So what's happening to the value of our gradient? It's going from positive to negative, isn't it? Yeah. So the rate of the change is negative, yeah. And in our minimum point, it went down, it flattened out, and then the gradient started to rise. So our gradient is therefore going from negative to positive, yeah. So these are our two most important ones that we use quite a lot. Maximum, so in the maximum, our gradient's going from positive to negative, and we could calculate the value of the gradient just to the left of the point, at the point, and to the right of the point. We know it's 0 at the point, but to the left it should be positive and a maximum, and to the right should be negative, yeah. And if we were looking at the minimums, well, if we calculated those on either side, it would be negative to the left hand side of it, and then it would be positive to the right hand side. What about these inflection points? Well, the one we've drawn here is it's positive, the gradient's positive to the left hand side, it goes to 0 at the inflection point, and then it goes positive again. And we could do it having the curve the other way up. We could flip it on a horizontal reflection, in which case it will be going negative, then it would go flat, and then it would go negative again. So the difference with inflection points is that the gradient sign doesn't change. Yeah, it's negative on both sides or positive on both sides. So we could do all our calculations by just doing a sketch or calculate the gradients slightly either side and see what the result is. But is there a quicker way of doing it? Can we find another way of doing it? Okay, there is a way of doing it, and that uses the property we were just talking about, which is what's happening to the gradient. And what we could be interested in, what's the rate of change of the gradient? Yeah, rate of change. And rate of change of the gradient is, as we did with to find the rate of change of the y value to find the gradient is if we call m the gradient, it's dm by dx, yeah? And dm by dx, well, what are we actually doing? We're differentiating, we're doing d by dx of the m value, which we know is dy by dx. So what are we actually doing? We're doing the d by dx of the d by dx of the original y value, which is why we combine these two together, and it's often written in these terms. So we've got d squared because we did d there, and we've got dx squared on the bottom. So quite often you'll see this written as d2y by dx squared, but for a lot of you, you might actually find it more practical and more common sense to think about it as being dm by dx, i.e. it's the rate of change of the gradient, yeah? And that helps us, makes life very much easier if we're doing these calculations and understanding them. So if we started off with a function here, y equals x squared, yeah, so it's going like that. And if we want to find the gradient, well, we just differentiate that, don't we? So dy by dx is now 2x. So if we were looking at the gradient, we've now got a straight line, haven't we, going through the axis. There it is. It would have a gradient of 2, wouldn't it, that line? So when we differentiate and we look for the rate of change of their gradient, we're going to do d by dx of 2x. And if we differentiate 2x, we know we get 2, don't we? So we know that all the time the rate of change of the gradient is 2 in this example, and that's our d2y by dx. So a quick way of finding d2y by dx is calculate your m first and then differentiate your m to get your value. Okay, so I hope that gives you an explanation of how that works. Let's have a look at some examples of how we could use this. Yeah, let's have a look at this function y equals x cubed minus 3x. We could sketch it as I've done on the left hand side, and we would roughly see that there's a maximum over this side and a minimum over that side as it goes to this sort of inverted reflected S setup. But what do we want to do to find the points, the stationary points? We want to differentiate it first. So dy by dx, the gradient of this curve, is therefore going to be x cubed goes to 3x squared, and 3x minus 3x becomes minus 3, doesn't it? So therefore the gradient, the stationary points, we want that to be equal to 0. So that means that 3x squared minus 3 must equal 0, which means that x squared must equal 1, and therefore x must be plus or minus 1. So we've found our two stationary points, haven't we? That makes sense looking at our diagram here, is that there's one at minus x equals minus 1, and there's one here at plus 1. That makes sense, doesn't it? Okay, now let's use the second order derivative to calculate the gradient, sorry, whether these are maximum or minima. Okay, so, well, we found m just now, didn't we? It was that 3x squared minus 3, that was our gradient, and now we're going to differentiate it, aren't we? Because we're interested in the rate of change. So the first term, 3x squared, becomes 6x, and the differential of minus 3 is going to be just 0, isn't it? So we now know that the rate of change of gradient is 6x. Now we know our two stationary points, so x equals minus 1, x equals plus 1. So when x equals minus 1, the rate of change of x, gradient, sorry, with respect to x is minus 6, isn't it? Because that's 6 times minus 1 gives us minus 6, yeah? So that rate of change is negative. So it's going from something positive, a gradient, to a negative gradient, yeah? It's going from a plus to a minus because it's a minus. So therefore we're looking at a maximum point, aren't we? Now, when x equals 1, then the rate of change of gradient is going to be plus 6, because that's 6 times up here in our expression, isn't it? 6 times plus 1. Here we go. So that's plus 6, isn't it? So our rate of change is greater than 0. And what we're looking at is a change where the gradient has gone from negative to positive. Yeah, the rate of change, the change is positive, isn't it? Therefore, we're looking at a minimum point. Okay, So let's incorporate that in our diagram. So we found for ourselves that we have a maximum point on the left hand side, and that we know that x is -1 at this point, and we can find that the y is 2, therefore the coordinates are -1, 2. So that's our maximum point on the left hand side. And on the right hand side we have a minimum point. We found that our x value is +1, and if we substitute that in, we find that our y value is -2. So there we are, we found our maximum and our minimum. Remember that on this side dm by dx is less than 0, and on this right hand side our dm by dx is greater than 0. So that deals with maximum and minimum points. Let's have a look at an example that will help us with inflection points. If we take our function now as being y equals x cubed plus 4 and differentiate that, we find dy by dx, that's our gradient m, is 3x squared. So the stationary point is where the gradient's going to be equal to 0. So that means 3x squared is going to be equal to 0. Therefore x squared is going to be 0, which means that x is going to be 0. So we've now got one stationary point, not two as we had in the previous one, just one. Okay, now if we look at the second order derivative, the rate of change of gradient, we know that our gradient is 3x squared, and if we differentiate that we end up with 6x. And when we're at our stationary point, we worked out that x equals 0 is our stationary point. So the value of 6x when x equals 0 is 0. So the rate of change of gradient is 0. What's that telling us? That the rate of change equals 0. So we're looking at an inflection point. Okay. So if we add that to our diagram over here, we can see that our inflection point was at x equals 0, wasn't it? And we can substitute that in and find out y equals 4, 3. And what we're actually saying is at this point, dm by dx equals 0, yeah? The rate of change of gradient is 0. So there we have it. So a quick summary at the end here. Stationary points. We've got three types of stationary points: maximum, minimum, and inflection points. And all of these stationary points, the gradient, the rate of change, equals 0. At a maximum point, like this one over here, the rate of change of the gradient, that's dm by dx, going to be less than 0 because it's going from gradient's going from plus to minus. For minimum point, the rate of change of the gradient is going to be greater than 0 because we're going from minus to plus. And at an inflection point, the rate of change is going to be equal to 0. Yeah, because we're going up, because at that point it's going absolutely flat. The rate of change is going from plus to plus, yeah? So we end up going back to where we started. Okay, hope that's of use.